So quick recap, everything that we've done so far. We just saw that iterated structures like these are good for analyzing data with short time dependence in the past. So for instance, if you assume that your current prediction depends only can be made based only on the past few observations, then a network structure such as this one would be able to make the predictions just fine. On the other hand, if you needed a structure that, so these were time delay neural networks, convolutional neural networks, and such like, right? On the other hand, if you want to analyze time series data with long-term or even infinite dependence on the past, then you need recurrent structures. So you want something where you have some state variable that keeps passing information on. In some variants of the model, the state variable was the output itself. And this recurrence made sure that you retain information about the infinite past. So these were your recurrent neural networks. Now, the amazing thing about recurrent neural networks is that it's not only for time series analysis that these are really, really effective. There are some problems where a recurrent neural network can do what a static structure a fixed size static structure cannot, or the same size cannot. So consider the simple problem. Addition, right? So suppose I want to add two n-bit numbers, and I want to do this using a standard multi-layer perceptron. So you have layers, and all the outputs come out at once. How large would this network be? So I'm giving you, I have a network of this kind. If I have only one layer, right, then that one layer must account for every possible combination of inputs. It's going to be exponentially large in the number of bits. If I'm allowed two layers, it's still going to be very large. How large is it actually going to be? Think about it, right? I have two n-bit numbers. The output must be n plus 1 bits, correct? And all that's going in are these two n-bit binary patterns. And you have to create a multi-layer perceptron which does this very simple operation of adding things. How complex will that be? I'll let you think about it. It gets to be large, right? It would be but then, even if you do come up with a network of this kind, suppose you design a network that works on two n-bit inputs, and now you want to add two n plus 1 bit numbers. Will it work? Obviously not. It doesn't even take the n plus 1th bit, right? So now here is a problem which is kind of complicated for simple in the simple case and intractable in the more complex case. But then let me replace this with a trivial recurrent network. This is an adder, right? If I operate this, if I work on the inputs 1 bit at a time and treat it as recurrence, then all I need is a little XOR. The carry goes over. So I have 3 bits going in, 2 bits coming out, and I can operate on the inputs 1 bit at a time. There's no restriction on the number of bits in the input, and the entire thing can be done with half a dozen units, right? So simple problem. We actually took something that is a static problem, namely that of adding two n-bit numbers. And this turned out to be really complex for networks that was designed for static problems. But then when I replaced it with a recurrent network, voila, the whole thing suddenly became much simpler, right? So also here's another problem, the parity problem. What's the parity problem? Anybody remember? What was the parity problem? You count the number of ones, right? If you're counting the number of ones, that actually ends up just being an XOR. Parity is an XOR. And how large was the parity problem if you just had one layer, one hidden layer? Exponentially large, right? Now, even if you have more than one hidden layer, if I'm counting if I want you to build me a network which takes an n-bit number and produces a 1 if the number of ones is even, and a 0 if the number of ones is odd, it's going to be very large. It may not be exponentially large if you make it deep, but it's still going to be very, very large. And furthermore, if I have a network that works on n-bit inputs, there's no way it's going to actually operate on n plus 1 bits. But now suppose I redid this using a recurrent neural network. How would I do this? Anyone want to take a guess? What would this look like if I used recurrence? I can see the answer, popping out. Tell me. It's a simple XOR. That's all it is, right? If I do this using recurrence, here is my network. That's just a little XOR. It takes two inputs. You operate on the input 1 bit at a time. If the 2 bits are the same, you don't flip. The output doesn't flip. If the 2 bits are not the same, the output flips. And at each time, it takes the output from the previous time and the current bit, and just operates on 2 bits at a time. And this complicated network became trivially small. In fact, everything that we did in class 2, lecture 2, became invalidated by this tiny little network, right? So you can see that recurrence is very powerful. You can take even what look like static problems, and if you deal with them using recurrence, then then you can actually end up with far simpler structures than you would if you actually wanted to operate on the original static problem, right? So that we've seen. Anyway, continuing with the story so far, recurrent structures we saw can be trained by minimizing the divergence between the sequence of outputs and the sequence of desired outputs, right? Through gradient descent and backpropagation. And here we actually did define the divergence between the complete sequence of outputs and the complete sequence of desired outputs. We also saw that you can have different kinds of recurrence. You don't need just a single step recurrence. You can have multi-step recurrence, like in the first case, you're recurring over 2-time instance, or in the figure below, the recurrence is over 3-time instance. So the current hidden state is looking at the previous hidden state, the hidden state value 2-time instance in the past, and then again 3-time instance in the past, and so on. And all of these would have to be properly initialized. So far it's all very good. Now the question is, I've given you a model, can you trust it? How do you know that it's actually going to behave in a responsible and reasonable way, right? What do I mean by responsible and reasonable way? To try to motivate this question, let me start with this problem. This one we've seen. This is not the recurrent neural network. This is just a simple iterated structure, a time delay version, right? So will the output ever blow up if the inputs are bounded? Using any of your conventional activation functions which don't go to infinity for finite input, will the output, if the inputs are all bounded, will the output ever blow up? Nope, right? Because you're going to have some weighted sum of a small number of finite number of values. So each of the values, if these guys are bounded, or if all the x's are bounded, and let's say each of the x's have an upper bound of some c, and let's say the weights have an upper bound of some d, then the total input coming is going to be no more than 4cd in this case, right? That is going to be bounded. I put it through an activation. The activation is going to be output is going to be bounded, and so I have a bunch of bounded inputs going into the next layer. No matter how you do it, eventually the output is going to be bounded. So this is what we will call a bounded input, bounded output system, BIBO system, right? Now BIBO or the system is said to be BIBO stable. Time delay structures have bounded output if the function f, the activation function, has bounded output for bounded input, and if the inputs are bounded, right? So bounded input, bounded output stability is a highly desirable characteristic. You don't want your network to blow up, because as you're continuously processing input, if the output just simply blows up, then that's not very good, right? Now let's go and look at recurrent structures. Is this guy BIBO? Will this necessarily be BIBO? We can't say, right? Now in one case, if I have all the activations, hidden activations and output activations are sigmoids, then you know the output is never going to go to infinity. It's going to be bounded at 1. But that is not this. But that's still a problem. It's not merely boundedness that's of interest to me. If the output saturates after a few time instants, that's just as bad, because now the output has become uninformative, right? So thinking about boundedness is the same as thinking about whether the output is going to be meaningful, whether it's going to saturate. So let's think about the boundedness case. We will actually assume there are no activations to understand how the whole thing works, and assume all activation functions are linear. Because if the linear system explodes, then something with an activation function is going to kind of saturate, right? So we'll also look at we'll look at nonlinear systems in a little bit. So let's analyze recurrence. Now, the actual recurrence over here is not in the output. The recurrence is not in the input. The recurrence is in the hidden layer, the H's, right? So all we really need to do is to analyze the H's and the how the H's behave. So that's what we're going to do. And we're going to assume, for simplicity, a single hidden layer. And we're going to assume that all the activations are linear. So in other words, we're going to use the good old Streetlight effect. We know how to analyze linear systems. We know how to analyze simple systems. One-layer systems are easy to analyze. We are going to sort of assume that any analysis we come up with on these simple systems will inform us about the more complex system, right? So here is the network we're going to analyze. All activations are identity functions. We have one hidden layer. So which means that the affine combination to the hidden layer, any hidden unit, is a weighted combination of the hidden values at the previous time plus a weighted combination of the current input. So the current input going down, the previous input coming from the right, and there is no and the output is simply the affine combination itself, because we are assuming the activation is just an identity function. There's no non-linearity, right? This is a linear system. So look at so I can literally write over here HK is, well, how did I write that? WH HK minus 1 plus WX XK. This is my hidden activation, right? Now let's see how the whole thing works. So I have HK equals WH HK minus 1 plus WX XK. Now HK minus 1 in turn is exactly the same thing, right? HK minus 1 is simply going to be WH times HK minus 2 plus the WX times the input at K minus 1. So what I have done is this guy this was HK, this was HK minus 1. This one captures this equation, right? This relation. But the second one actually captures this relation, right? So now I can plug this HK value into the formula for this HK and write this HK in terms of these two inputs and HK minus 2. Correct? And that's exactly what's happening over there. So if I actually plug those two guys in and I write HK in terms of HK minus 1 and HK minus 2, it's going to be, just plug it in, you see what's happening. The weight matrix applies once here, it applies a second time here, so you're going to get weight matrix squared times HK minus 2 plus weight matrix. So this WH applies to this guy. So WH times WX XK minus 1 plus WX XK. Okay? Now I can take this step back. You see what I'm doing over here? I just sort of expressed this HK in terms of these three terms. This one is not going to be multiplied by the hidden connection weights matrix. This one is going to be multiplied by the hidden connection weights matrix once. And then you have HK minus 2, which is multiplied by the hidden connection weight matrix 2 times. Right? Now I can take that one step back. And now I can talk about it in terms of HK minus 3 and these three x, these three x's. And I can keep moving back in this manner until eventually I'm expressing hk in terms of the initial h minus 1 and the sequence of inputs, right? And that one is going to look like so. That is simply hk. If I move all the way to the beginning, that is simply going to be the weight matrix raised to k plus 1, because the weight matrix is going to be applied k plus 1 times, applied to the initial condition of h, plus wh raised to k times wx x0, right? Every time x goes in, it's multiplied by this weights matrix. So x is always multiplied by the x matrix, by the input weights matrix, right? So that's just a straight up expansion. Now consider any single term over here, this guy. That one, if I just drew the entire figure out, right, like so, if all of these inputs were 0, and if this guy, which is h minus 1, was also 0, and if I just had an x0 over here, that term is simply the response to the system if the x0 went in and came out here, right? So in other words, every single term over there is the response to a single x, assuming everything else is 0. And so I can write that as this: hk is the response of the entire system to the initial condition, assuming all the x's are 0, plus the response to just x0, assuming everything else is 0, plus the response to x1, assuming everything else is 0, and so on, right? And so I'll write that term like so, which is hk of x0 is simply going to be as a response that you get when I apply an input x0 k time instance later. That's just a shorthand notation. But then it's, this x is just a scaling factor. So when I say wx, wh raised to k, wx x0, this is the same as saying wh raised to k times wx times 1 whole thing multiplied by x0. Think of it in scalar terms, right? So I can say this is the same as the responses, the sum of the responses to a unit input at various times, each of them scaled by a corresponding x value, right? Now the purpose of all of this, right, writing all of this, means that in order to analyze the response of the entire system, I just need to analyze the response to a single input at time 0, because everything else is basically the same thing, right? Because it's just a linear sum. So that's what I'm going to do. Because we're using the principle of superposition. If I understand how it's going to respond to a single input at time 0, it tells me how it's going to respond to a single input at any other time. And so I can just add all of these responses up. Now, so the only thing I'm really interested in anymore is this guy. When I have x0 equals 1 and xk equals 0 for k not equals 1 and h minus 1 equals 0. If I understand this behavior, then I know how the system is going to respond. Now another way of thinking about it is, how well does it remember at an input at time 0? This is what we really are interested in, right? Remember when we showed the programming example in the last class, when you open a curly brace, the first thing that happened was an open curly brace at time 0. You had to remember that this thing was opened until you finished the program, and then you had to close the brace. So it's a question of how well does it remember something that happens at time 0. So consider a single scalar linear recursion. What is the response of the system as when you have a single input at time 0 and no other inputs? So at the first time instant, it's simply going to be c times x, x0, right? Subsequently, the only values that remain are the h values, because the remaining x's are 0. So the response at time t, h0 of t is the response of the system at time t when you get a single input at time 0. That's simply going to be w raised to t times c times x0. Everybody clear about what's happening over here? How will this behave? What happens if w is greater than 1? What will happen if w is greater than 1? It will just blow up very quickly, exponentially fast. Right? What happens if w is less than 1? It's just going to fall down really fast. Right? Either way, it's going to either blow up or it's going to vanish. Which means that this is really, memory is going to be dependent on the actual weight values, how well it remembers things. Now I can think of vector recursions. Vector recursions are basically the same thing. I can replace the scalars by vectors. Now if x0 is going to be an input vector, right? And the response at time t is simply going to be w raised to t times c times x0, correct? Where this is just, everything is now matrices and vectors. But then here is something that you want to remember. I can write the weight matrix as some u times my lambda matrix times u inverse. This is your standard eigen decomposition, correct? And that, so you have wu equals lambda u. That's your where u are the eigenvectors of your weights matrix. Now if these u vectors span the space, then any input x can be expressed as a linear combination of these eigenvectors, correct? So I can write any h as some a1 times u1 plus a2 times u2 plus a3 times u3. I'm just going to write it, expand it in terms of the eigenvectors. So what happens when I multiply this guy by the matrix W? That's simply going to be a1 times, so WH, so I have h equals a1 x1 plus a2 x2 and so on. So WH, these a's are scalars, right? It's a1 wx1 plus a2 wx2, wait, u2, this should be u. These are my eigenvectors, right? But what is w times u1? Because u is an eigenvector, it's simply lambda 1 times u1, right? So this is simply going to be a1 lambda 1 u1 plus a2 lambda 2 u2 and so on, right? That's exactly what we've written over here. Every time I multiply this by w, all that happens is this term, I get an extra lambda. Because a is, right, if I multiply this again by w, that's simply going to be a1 lambda 1 squared u1 plus a2 lambda 2 squared u2 and so on. So when I say w raised to t times h, basically the result is I have w raised to t times h equals summation over all of the eigenvectors ai lambda I raised to t ui. This is your standard Langstroth's expansion, right? So now what does this mean? Now each of these u's, look at this geometrically. Every vector, think of a case where in 2 dimensions I have 2 eigenvectors, u1 and u2, okay? And any eigenvector, any vector can be expressed as some u1 scaling factor u1 times scaling factor times u2, okay? Now the first time it's multiplied by w, this component is going to get multiplied by lambda 1. This component is going to get multiplied by lambda 2. Assume lambda 1 is greater than lambda 2. So then this is going to become, this gets multiplied by a lot, this gets multiplied by somewhat less, right? The resultant is going to end up closer to this guy than it was in the first place. As I keep multiplying it more and more times by w, the eigenvector with the longest lambda will dominate. Eventually, the only thing that's going to remain is the eigenvector with the largest lambda, right? So in effect, eventually, in the end, all you're going to get is am raised to times lambda m raised to t times the principal eigenvector, right? So now this tells you something very interesting. I really need to know, in order to understand how this recursion is going to behave, all I need to know is to look at the largest eigenvalue, because the long-term response is entirely controlled by the largest eigenvalue, correct? So for any input for large t, the length of the hidden vector will expand or contract according to the tth power of the largest eigenvalue of the hidden layer weights matrix, correct? And you can always have an input which has no component along the largest eigenvector, in which case it's going to expand according to the second largest eigenvector, but we won't, that's just a minor issue. But here is what happens. I'm going to say that lambda t raised to tu corresponds to am lambda m raised to tu, right? If lambda m is greater than 1, if the largest eigenvalue is greater than 1, what's going to happen? This is going to blow up exponentially. If the greatest eigenvalue is less than 1, it's going to shrink, right? So here are the behaviors that you will get. I'm using this simple recursion, and I'm actually showing you plots of the length of the hidden vector h as a function of the iterations. And here the maximum lambda value is 0.9, and you have other lambda values, right? So the blue line shows you just the length of the component along the largest eigenvector. The red line shows you the overall length of the vector. And you can see what happens. The overall length of the vector eventually simply becomes the length of the largest eigenvector, and that in turn simply falls off very quickly to 0 as your t becomes greater and greater, right? In the second case, I have two different cases. I have lambda max is 1.1, and you can see that the length of the hidden vector simply blows up, right? Over here, the lambda max is exactly 1, and it just stays constant. Now in the second case, I have these two things oscillating. Why are they oscillating a little bit? And, pardon me? No. It has to do with the fact that your eigenvalues and eigenvectors can be complex, right? So when you get complex eigenvalues, you're going to get an oscillatory behavior, but the length is sort of going to keep increasing. And in the third case, the eigenvalues and eigenvectors are real, so it's going to sort of monotonically increase. So here's what will really happen. In the first case, in the first two cases, you have complex eigenvalues. The second case, you have real eigenvalues. But what you will see is this. Long-term behavior depends entirely on the eigenvalues of the hidden layer weights matrix. If the largest eigenvalue is greater than 1, the system response is going to blow up. If it's less than 1, it's going to die down to 0, right? And if you have complex eigenvalues, you will have some oscillatory response, but the magnitudes are still going to blow up or die off. Either way, it's not a very great thing. Now, this is just talking about not using non-linearities. This was for a linear system, right? What happens if I introduce non-linearities? Now, the first thing you observe over here is that if I only had had linear activations in my hidden layer, the system doesn't really have a memory behavior, does it? If you give it some input, whether it remembers it or whether it doesn't remember it, really depends on the weights matrix. If the lambda max is greater than 1, the memory is going to explode to infinity. If it's less than 1, in 10 steps, it's going to die off, and it's going to forget what happened. Right. Now, so simple linear response is maybe not great. So let's see what happens with non-linearities. Here it's the same thing. Now I'm doing this for a scalar input. And for the scalar input, the function f, this is the same equation as before, except that the hidden response, the response h at each time is obtained by applying an activation to the affine combination. So we have the function f is an activation. We are looking at 3 different activations. One of them is a sigmoid, the other is a tan h, and the third is a ReLU. Okay, and see what happens with sigmoids. Depending on the weights, the magnitudes of the weights value, the sigmoid very quickly saturates to some fixed value. So here I've initialized the h with 1, and the sigmoid very quickly saturates in like 2 or 3 steps, regardless of the value of w. The number of steps it takes to saturate is very few, right? If I use a tan h activation, it doesn't saturate quite as fast, but it still does have, it has better memory behavior than the sigmoid itself, but it still eventually sort of ends up saturating. Now in the case of a ReLU, I'm assuming the weights are positive. If the input is positive, if the weights are positive, it's going to behave like a standard linear activation because the negative side doesn't really kick in. The thing is going to blow up or die off just as before, right? Now, same thing, instead of initializing it with +1, I initialize it with -1. Now this is the interesting thing, right? Regardless of whether I initialized it with a +1 or -1, the sigmoid went and saturated at the same place. And the place where it saturated depended on w, not on the input, right? Which means what the sigmoid activation does is that what is remembered is not what is, not a function of the input, is just characterizing the weight somehow. So the sigmoid activation is not a great activation for the hidden layer, right? What about the tan h? The tan h now still has similar behavior. It kind of saturates, but because it sort of retains some information about the input for a longer period of time, the tan h is a better activation for the hidden layer than the sigmoid itself, because the tan h actually retains memory for some time, but eventually even the tan h is going to saturate, simply because of the value at which it will saturate is going to depend on just the weight and not on the input. So if you had to think of the recurrence as retaining some memory of past events, which of these 2 activations would you use, tan h or sigmoid? Clearly the tan h, right, because it's remembering things for longer. The ReLU, if the input is negative, if the weight is positive, there's nothing remembered. It just goes to 0 because it's cutting off all negative values, right? Now this is for a scalar equation. Let me take this again to a vector equation. Here I've done as the same thing. Now I'm applying it to vectors. What I'm plotting is the length of the vector, hidden vector. I've initialized this now with a unit vector where all components are +1. And once again, you can see that if I use a sigmoid activation, the length of the hidden vector very quickly saturates to a fixed value, right? If I use for different weight values, if I use a tan h activation, things are remembered for somewhat longer, but they also saturate, and the ReLU can either blow up or die down once again, depending only on the principal eigenvalue of the weights matrix. And the same thing with a different activation. Instead of using a positive vector of all 1s as my initialization, I use a negative vector of all -1s as my initialization. And the reason these values are all positive is that I'm plotting the length. And you can see quickly that it's actually, when I use a sigmoid activation, once again, it simply saturates, right? In the case of the tan h, it remembers things for a little while, but eventually that too saturates. The ReLU can either blow up or die down, right? So what is the conclusion from all of this? First, if you're looking at stability, if you're looking at Bibo analysis, if you want to do formal stability analysis, you have to look at something more than simple intuitions based on figures. You can do it formally using Lyapunov functions and Roots criterion and so on, the conclusions you're going to get are very similar. Only the tanh activation is going to give you any kind of reasonable short-term memory behavior. But none of them actually have long-term memory. In general, bipolar activations, which can take both positive and negative values like tanh, have a better memory behavior than unipolar activations like sigmoid or the ReLU. But in all cases, the best case memory is short and things are forgotten exponentially fast. Right? Eventually the response stabilizes to some value which doesn't depend so much on the input but more on the weights matrix. Now is that really the response you want? You're trying to remember things forever. Whether you remember things forever or not must depend on the input and not on the parameters of the network. What you remember must be the input, not the parameters of the network. So this is not a great response, right? Now you can try to do this, you can try to sort of account for this by adding deeper recursions, where instead of just looking one step in the past, I'm looking 2 steps in the past or maybe 3 steps in the past. So here I have 2 examples where I'm looking 2 steps in the past and 3 steps in the past. And the behavior is pretty much going to be the same. You're going to get slightly more complex oscillatory behavior initially, but the long-term response is still eventually going to depend only on the parameters of the recursion and not so much on the h values itself, right? How well things are remembered is going to depend on the parameters of the recursion. So, and even here, the stability analysis with nonlinear activations, it's straightforward, but the point is the overall conclusions don't really change. So here's the story so far. Recurrent networks retain information from the infinite past in principle. In practice, they tend to blow up or forget. The memory of the network depends largely on the weights, the principal eigenvectors of the weights matrix, and also on the activations if you have nonlinear activations. And these can have a much more significant effect on what is remembered than the input itself, which kind of makes the whole makes the memory behavior of the recurrence somewhat suspect, right? So RNNs, they're excellent time models for time series analysis, prediction, classification, what have you. They can even simplify problems that are difficult for MLPs. But the basic RNN structure has this problem. The memory is really not all that great, right? Things tend to be forgotten in a manner that depends on the parameters of the network rather than on the input. So there's a second problem. Besides the fact that the memory is not really a function of the not merely a function of the input, but also a function of the parameters, right? And it largely tends to be more a function of the parameters than of the input. That's one problem. There's a second problem that's about how well you can learn things, and this is the so-called vanishing gradient problem. Now, this is not just specific to recurrent networks. This holds true for any sufficiently deep network. And to understand it, let's look at a deep network, right? If I have a network with many, many layers, the output is just basically a nested function, right? The output of the network is the output activation applied to a weighted combination of the activation of the penultimate layer, which in turn is just the activation applied to a weighted combination of the second to last layer, which in turn is a weighted combination of the third to last layer, and so on. Affine combination, not so much weighted, right? So, and the error, the divergence, in turn is a function of y, so the divergence too is just this long nested function. We know how to deal with the derivatives of nested functions. You're going to use the chain rule, correct? Let's see how this works. So in general, this notation is horrible. I should really be using vector notation on top. But if I have a derivative of the function of a function of w of g of x with respect to x, the chain rule says that's simply going to be the derivative of f with respect to wg times the derivative of wg with respect to g times the derivative of g with respect to x, which is going to be, so in other words, the gradient of f with respect to x is the gradient of f with respect to z, where z is simply w times g, times w, which is the gradient of w times g with respect to g, right? Derivative of w times g with respect to g, right? Times the gradient of g with respect to x. This is just the chain rule. We've seen it many, many times. Okay. Now let's see. So this guy is a this guy is the Jacobian matrix of f of z with respect to z, is it? Well, I may have some. That's I'll have to go back and check the slides, but you get the idea. Okay. Now let's go back and see how this translates to this particular derivative. The derivative of the divergence with respect to the intermediate values in a network. Now when I'm performing back propagation, what am I doing? I'm starting at the outermost layer. I compute a divergence, and in order to compute the derivatives with respect to all of the weights, I have to compute the derivatives with respect to the outputs of every one of the intermediate layers, right? In other words, I need to be able to compute the derivative of the divergence with respect to each of the f's, right? And so let's look at the derivative of the divergence with respect to fk. Now just using the chain rule, that is going to be the derivative of the divergence with respect to its argument. So anytime I write something like this, if I write derivative of whatever, let me call this h, this means that h is a function of something which I'll call z, and this is simply the derivative of h with respect to the argument of the function, which can itself be very complex, right? So here, if I use the chain rule, that's simply going to be the derivative of the divergence with respect to its argument, which will be in this case a row vector, times the derivative of f with respect to its argument, times the derivative of the argument of f with respect to the previous f, which is simply the weights matrix, times the derivative of f n minus 1 with respect to its argument, times the subsequent weight matrix. The chain rule just gives you this very simple chain of operations, right? So again, I can it doesn't really need a lot of working out. This is fairly straightforward. We've seen this several times. Now over here at each point, every term, the first term is a row matrix. Everything else, first term is a row vector. Everything else is a matrix, because the derivative of any f is the derivative of that f with respect to its argument, right? And f's, as we saw, these derivatives, as we saw, are just Jacobians. Jacobians are matrices, right? So every term except the first term is a matrix. The derivatives of the f's are Jacobians, and the weights, of course, are matrices. So every term over here is a matrix. So in order to understand how this behaves, we just have to take a little look at the matrix algebra itself. Consider these guys, f of n's. Every one of these is a Jacobian. And what do these Jacobians look like? Now, in a typical hidden layer, you have scalar activations, meaning every unit is computing its activation without responding to the other units, right? Without considering the other units. So the Jacobian matrix is going to be a diagonal matrix. Now secondly, the Jacobian matrix, because these are hidden units, the Jacobian matrix is going to be square. It's diagonal. Now what about the diagonal terms? The diagonal terms are going to be the derivatives of the activation functions, which could be sigmoids, ReLUs, or tan h's. What is the maximum value that this derivative can take? What is the largest derivative of a sigmoid? It's going to be 1, right? What is the largest derivative for tan h? Also 1, right? What is the largest derivative for ReLU? Also 1. Pretty much all of your activation functions have a slope that maxes out at 1, right? So in other words, these diagonal terms of this Jacobian are all upper bounded at 1, right? So this means if I actually, this means that when I multiply a vector by this Jacobian matrix, what's going to happen to the length of the vector? Every component is going to be multiplied by a term that is not greater than 1, right? The length of the vector will either stay the same or shrink, correct? So when I go out here, so just to give you an idea, here are the various activations functions. This particular one is a sigmoid. This is a tan h. You look at what the derivative looks like. The derivative goes from 0 to 1 and back to 0, right? So the diagonal terms are all going to be less than 1. Multiplying by the Jacobian is going to shrink the vector, which means that as you are doing your back propagation to compute the derivative of the divergence with respect to any fk, you start off with the derivative of the divergence with respect to y, the output. Then you're going to multiply that by a Jacobian. What happens? That thing shrinks, right? Then you multiply it by a weights matrix. Something happens. Then you multiply it by a Jacobian. It shrinks again. Then you multiply it by a weights vector. Then you multiply it by a Jacobian. It shrinks again, right? So every time this derivative encounters a Jacobian, the length of the derivative shrinks, right? But then that's not all of it. There are the weights vectors. What happens when you multiply these things by the weights vectors? Does the length increase or decrease? What will happen? You can't really say, but it's going to depend on the largest singular value for the weights matrices. So along the directions where the singular values are large, this vector is going to increase in length. Along the other directions, it's going to shrink in length, right? That's what happens when you multiply it by weights matrix. So for every single step, the result is going to the product is going to increase in some very specific directions, and every other direction is going to shrink, which means components are going to begin going to 0, right? So the overall product, repeated multiplication by these weights matrix, is either going to result in explosion if the intermediate values are pointing in the direction of the maximum singular value, and if they don't, they're simply going to shrink. Now something that happens is, because each weight matrix is different, if the result of one weights matrix increases the length along a particular singular value, the next weights matrix may not have a singular value in the same direction. It's going to shrink it right back. So things are more likely to shrink than to increase in length, right? Unless you have recurrent neural networks where all the weights matrices are the same. But regardless, you're going to have, so the real behavior you want to look at is the behavior of, the product of the Jacobian and the weights matrix can be thought of a matrix, and what happens to the derivative really depends on these guys. In general, the chain product will expand the derivative in directions where each stage has a singular value greater than 1, and it's going to shrink the derivatives in other directions. And things are more likely to shrink than expand, because even if you increase the length in one direction, when you go to the next stage, that's not going to be a direction of increasing length. It could be something else, and things will shrink, right? So as you go through the chain, things will keep shrinking. So just to give you an idea, so let's say I have some derivative with respect, so let's say I have derivative of the divergence with respect to y, that's at the very end, and so let's say these two are my singular vectors, and this is an expanding direction, this is a contracting direction, and this is my derivative with respect to y. So then what will happen is that after it's done, it's going to become longer in this direction, and it's going to be longer in this direction and shorter in this direction. So it becomes something like this. I go to the next stage, and the next stage is going to have a completely different set of singular values with different directions in which they expand or shrink, because every stage is different, right? And furthermore, the singular values and singular vectors depend on the Jacobian matrix, which itself depends on the input. So now this vector, which is like so, suddenly it's going to shrink. It's going to become like so. And then you go to the next stage and you have two other singular vectors, and then it's going to shrink again. Occasionally some terms will expand, the rest of them are going to shrink. So eventually what will happen is that the gradients, as you keep going back through the network, the gradients can either explode if by chance you keep pointing in the direction of singular vectors with singular values greater than 1, or if the whole thing is just going to shrink. Right? It's going to keep shrinking and shrinking and shrinking. The further back into the network you go, the more it's going to shrink. And so you're either going to end up with vanishing gradients, things that become really small, or on occasion you're going to have an exploding gradient where things just keep growing and they blow up as you go back through the network. Right? So, which means that you're going to get either insignificant gradient updates because the gradients are 0, or you're going to have unstable gradient updates because the gradients end up being reported as being too large. The thing has blown up, right, for any given step size. So this is not really a very good thing for training, and you will actually encounter this in your homeworks as the network becomes deep. If you don't have things like skip connections or residual connections, the network will really not be able to learn if it's very deep. Now, to see exactly how this works, I have this little figure from a 19-layer MNIST model where I just used an MLP. So 19 layers is pretty deep, right? And the MLP is 1024 units in every layer. And so the figure shows you the magnitude, the length of the gradient of the weights vector at each layer for the various layers. So I have 1024 units. So therefore I have 1024. I have 1024 gradient length values, right? This is the output. The lowest layer is the output. The highest layer is the input. And you can see what happens to the gradients as I go through the network. Near the output, the gradients all have significant value. And then as you go towards the input, the gradient pretty much vanishes. It becomes 0. And this is reported on the log scale, right? It becomes very small. This is for an ELU activation. This is the gradient over an entire batch. This is for a ReLU activation. For an ELU activation, the gradients persist for a little while. For a ReLU activation, they vanish faster. For a sigmoid activation, they vanish faster still, right? And for tanh, it's even worse. So you can see what is happening over here. That as you go through the network, as you go backward through the network, the gradients disappear really quickly. Now that is batch grade. Those are batch gradients. Suppose I look at the gradients for a single instance as opposed to the average over a batch. What happens? The same kind of behavior. As you go backwards through the network, the gradients vanish and become really small really quickly. They disappear very fast, right? And you can see why. The math says that they must shrink. On occasion, something will explode. So what you will see is that if you look for individual instances, there will be some microscopic spots which are really large, which are not really being seen over here. The rest of them are just going to go to 0, right? So you have this issue. ELU activations maintain gradients largest, but in all cases, gradients effectively vanish after about 10 layers. The actual results may vary depending on your input and the network, right? So both batch gradients and individual gradients vanish. In reality, a small number will blow up, but because you have both exploding and vanishing gradients. So the recurrent networks retain information from the infinite past in principle. In practice, they are poor at memorization. The hidden outputs can blow up or shrink to 0 depending on the eigenvalues of the recurrent weights matrix. The deep networks also suffer from vanishing or exploding gradient. So you can't even learn these things properly. And that too depends on the behavior of the weights matrix and the Jacobians, right? So this means now recurrent networks are very deep networks. They're as deep as the input itself, which means if you want to actually learn how does an input at time 0 affect an input at time t equals 20, because the gradients will vanish, you're not really going to be able to learn this, right? The deep networks also suffer from the vanishing gradient problem. Now, there's a second aspect to it, right? We've talked about two different things. Things vanish when you're going forward in a recurrent network. So the actual forward pass makes information vanish. Things vanish when you're going backwards. When you're trying to learn the parameters, the gradients vanish. Overall, the behavior is really horrible in terms of actually retaining information from the past. It's not good. In terms of learning to retain information from the past, it's also not good, right? On the other hand, we are really interested in retaining information for as much time as is required. Now think about our programming problem. If I open a curly brace, until when must I remember the fact that a curly brace was opened? Until I actually close it, right? I can't let time decide, oh, I opened my program is 10 pages long, I don't need to worry about closing the brace. Your compiler won't like that, right? Things have to be remembered till they are properly closed. And what we find over here is that the networks that we have, their ability to remember stuff depends more on the parameters of the network rather than on the inputs. So this is not the kind of behavior we are really looking for. We want something a little more sophisticated, which leads us into the domain of mystery and magic, long short-term memory neurons, which are mysterious things, but not really. And we'll see why they are not mysterious, okay? So what we really want to do is to replace those guys, the combination of the Jacobian and the weights, or going forward, just the activation product of the activation and the weight. Either way is the same problem, right? Going forward is the product of the activation and the weight, which makes things shrink or vanish. Going backward is the Jacobian or the weight, which makes things shrink or vanish. So can we replace this particular thing which just doesn't fade or blow up, right? Now the problem with the standard recurrence is that as you go forward, things fade or blow up. As you take information backward, things fade or blow up. Can you replace them with something that doesn't fade or blow up? You really want the network that remembers arbitrarily long so that it can be recalled on demand, and the memory should not be dependent on the vagaries of the network parameters, but rather than an input-based determination of whether something is worth remembering or not and how much it must be remembered. So if I've opened a curly brace, I have to hang on to that memory until I close that curly brace. If I'm inside a loop, I have to retain the fact that I'm inside the loop till I've closed the loop, right? And I'm using programs as an example, but this pretty much applies everywhere, right? What this means is that I want my memory to not change. If I have some memory C, I want the memory to not change unless some switch which has looked at the input and decides that this memory is no longer worth remembering, decides to switch it off. So I have a memory C. I'm factoring a switch sigma, which is looking at the input. The memory C is going to say, I have opened 6 curly braces, or I've opened a curly brace, right? Now the switch sigma is going to say, oh, I've closed the curly brace. Then you can say you can forget it. And it's going to multiply it with a 0. And then it forgets it. But if I have not detected the curly brace yet, then the sigma will say, okay, there's no need to, I haven't closed this, continue remembering this, and so on. When I go backwards, the same thing happens, right? The derivative is exactly going to be the same kind of operation. The memories are going to be retained, and the manner in which the derivatives disappear or don't disappear again depends on the switch. So this is what we would really like to capture. That can be represented using this simple structure. The memory C, the history, is now captured by a memory C, which goes through uncompressed. There are no weights, there are no non-linearities, because we know that when you apply a weights matrix, things shrink or expand, not good, right? We know that when I apply a non-linearity, things saturate or horrible things happen, blow up or disappear. So we don't want non-linearities. All we want is for the memory to go straight through And then I want an extra term, a sigma, which is a gating term which tells you whether the memory should be continued or should be forgotten, right? But what does the gating term in turn depend on? So the gating term is going to be looking at the input. So this whole thing is what we will call the constant error carousel. It's called the constant error carousel. I don't know where the name comes in. They thought of it, I think it was originally introduced as an idea of carrying gradients backward. But the concept, regardless of the nomenclature, is very simple. You're going to have a memory C which goes through, and the memory's only job is to retain memory. All the nonlinear portions of the computation is done by other portions of the network. Okay? So here's what we would do. You want the switch which decides whether the memory must be retained or not to depend on what is currently in memory and what has been what the input is. So you want to know, do I already have a closed open bracket in my memory? And am I seeing a closed bracket? In that case, I'm going to ask you to switch it off. Otherwise, I'm not going to send you any information into the memory line, right? So the switch is going to see the input, and it's going to see what is currently stored in memory. Now, you may also want to have other cues to decide how to analyze the input to decide whether you're switching things off or not. And instead of just looking at so observe over here, when I do this, the hidden state is actually being computed not from the hidden state is being computed from the memory. The memory is going unmodified, but H is being derived from the memory. And so the switch here was looking at the H, right? The hidden state that was derived from the memory. You can extend it to you say, not only am I using the hidden state that's derived from the memory, I'm also going to look at the raw memory itself. You're just making the switch more and more complicated. You're making it look at more and more things. But the point of the switch is always the same, to analyze the input and decide whether what is being remembered has to be modified or not. Okay? This whole structure is the basis of the so-called long short-term memory neuron, which explicitly latches information to prevent decay or blow up. Now, in the following notes, I've borrowed liberally from this GitHub, I forget who, repository. So many other figures are not mine. Yeah.
So this gating is done for like RNNs. Is there like a similar version of it for like regular MLPs?
Pardon me?
Is there a similar version of gating for like regular neural networks or MLPs?
So again, you could apply the same principle, and yes, people have done these things. But the notion of trying to remember things is perhaps much more natural in time series than for analyzing static inputs, right? So, but you could apply the same concept pretty much anywhere else. So here is the standard recurrent neural network. The standard recurrent neural network, each unit looks at the current or the previous hidden output, hidden state, and the current input, combines them, and puts them through an activation. And typically we will use a tan-H activation because, as we saw, that retains memory best. In spite of that, using a tan-H, it's really not very good. The long short-term memory sort of ups the ante and makes things somewhat more complex. Here's what it looks like. You have a bunch of multiplicative gates that decide if something is important or not. And every line, by the way, represents a vector. You have things going into the page. And the structure looks complex, but when you actually begin analyzing it, it's very straightforward. This line here is the so-called constant error carousel. It's a remembered cell state. This is your memory. It's unmodified by any weight. It's only modified by switches and additions and subtractions, okay? Because you know that if you introduce a weight, bad things happen, right? So this is the constant error carousel. It carries information through only affected by a gate. And information may be added, which is also gated. Now the gates, these gates are simple sigmoidal units with outputs in the range 0 to 1, which controls how much of the information should be carried through, right? Now it's continuous valued because You can think of my memory as not just remembering whether I opened a curly brace or not, but how many curly braces did I open. And then if I see a closed curly brace, and I say, so far I've seen 18 open curly braces, and I'm seeing a closed curly brace, then multiply this guy by 17 over 18 to reduce the count of curly braces, right? So this is it's a number between 0 and 1. And so the first gate in the LSTM is the so-called forget gate, which tells you if the memory must be shrunk. In order to decide if the memory must be shrunk, it's going to look at the input, and it's going to look at the previous hidden state value, which carries information about what is being remembered, right? And then observe that we are distinguishing between the cell memory and the hidden state. The cell memory is just what goes through C. The hidden state is what is computed from C. Okay? Then the second component is an input detection pattern. First, say I've opened a curly brace. I need some pattern recognizer which determines if I've actually seen a curly brace, closed curly brace, right? For that, it has to look at the input, which looks at xt, but it also has to decide how much, it also has to decide, look at other information to figure out what it's looking for. So it's going to look at the hidden value of the previous state. And this combination actually goes through this tan H, which is the actual neuron, perceptron. But then something interesting happens over here. Even after you detect a pattern, you want to figure out whether this pattern is worth reporting to the memory or not, right? For instance, I have not seen any open braces. Is it worth reporting that I've seen a closed brace? Not worth it. So there's a gate which actually decides whether this pattern is worth reporting or not. And then once the pattern is reported, okay. Actually, this is not a forgetting, this is an input, right? So I've seen 17 curly braces. Now I've detected another curly brace which I think is worth reporting. Increase your count, right? So the memory now just sort of ups its count. So there are two components. One which tells it whether it's worth forgetting something that is already remembered, and second, whether the memory must be incremented because it's seen more of the same, and if it must be incremented. Then subsequently you have the hidden state. That hidden state is actually going to be compressed through a tan H, because that's what we use for computing the hidden states in recurrent networks, right? To give you the actual hidden state value. And while we are busy using gates everywhere, they also include an output gate which decides whether this hidden state value is worth reporting to future computations or not. There's a certain degree of unnecessary complication in this model. Some of the gates are look almost kind of too many, right? But the basic concept remains the same. Now, in all of these, the computations are only looking at the hidden state value. But for the gates, instead of looking at only the hidden state value, it's more reasonable to actually look at the raw memory. I'm remembering 17. I've seen 17 open parentheses. What should I do, right? If you compress it and if you put it through some funny compression function, the hidden state is a function of the memory. It's not the memory itself. So they actually add this extra connection, which is a direct input of the memory into these gates. This is only for the gates, not for any of the other computation, which they call the peephole connection. So this is the entire network. This is the entire cell with input, output, and forget gates and the peephole connection, right? Now this is a single unit. This unit, this little block, replaces a single neuron in your standard recurrent neural network. In a recurrent neural network, a hidden layer came in from the side, and input came in from the bottom. You combined them, you performed an activation, you produced an output which went up to the next layer and forward to the next, to the same hidden layer at the same level at the next instant. This is doing exactly the same thing, and the number of inputs and outputs are the same, except that you have one additional term, which is the memory that comes in directly, and that goes out, which may or may not have been modified. So here is the complete set of operations for the LSTM. You have these 3 gates. You have the forget gate, which operates on an affine combination of the past memory, the past hidden state, and the current input. You have the input gate, which also operates on an affine combination of the past memory, past hidden state, and current input. You have the output gate, which is the extra gate which multiplies the transformed or compressed memory from which the hidden state value is computed, which is now an affine combination of the current memory, the past hidden state, and the input. Now, again, like I said, some of these things are a little more complex than they need to be, but that's how it's defined. And now, of course, it's very simple. The first, this C tilde t is a term that decides if there's anything more to be added to the memory. And this is decided through this neuron, which looks at the past hidden state and the current input to decide if something has been discovered that is worth reporting. If that is worth reporting, then you multiply it by the input gate and add it to the current memory. And the current memory has been multiplied by the forget gate to decide if something must be forgotten in the first place, right? And the hidden value, of course, is simply going to be the compressed memory times the output gate. So all of this is just a set of simple equations that specify the operations of all of the units in the LSTM cell. So I have some pseudocode here. You should look it up. But the entire operation can now be compressed into can be dropped into a standard recurrent neural network code by, do you mind switching that thing off? It's disconcerting to me. Yeah. Okay. So I can talk of this in terms of a cell where I just define an LSTM cell which retains static variables, all the intermediate computations within the cell itself. It takes a certain number of inputs, which is the current memory, the hidden value at the previous time, and an input from below, and parameters, a set of all parameters, and outputs a hidden value and an updated memory, right? This is my cell. And the cell itself simply directly implements all of the equations that we just saw out here, okay? And now when I do a network, when I actually implement the network, it's very trivial. I can implement the hidden value at layer 0 as just the input. And then this is like your standard recurrent neural network. I go through the layers, and within each layer, I'm computing the output of a cell as a function of the memory at the previous time, which is the memory would be initialized to 0 because there is initially no memory, the hidden value at the previous time, the hidden value at the current time at the lower layer because that's the input coming from below, and the parameters. And then finally at the output layer, you just compute the affine combination and the output from the affine combination. So this is just your straight up LSTM. This is a very simple trivial implementation of the LSTM, and you see that as far as the code is concerned, although the whole thing looks kind of complex, it's not really that complicated. It's very straightforward and fairly simple, right? Now, so going forward is easy. What about going backwards? Going backwards, it turns out, looks horrendously complex. How are you going to compute the derivatives? You have this really horrible structure. How are you going to compute the derivatives of the divergence with respect to ct minus 1, ht minus 1, and xt, given the derivatives with respect to zt, ct, and ht, right? Now, if you look at the derivatives with respect to ct, that has many contributions. You have the contribution of this path. I won't actually read it out. You have also the contribution of this path. You have the contribution of this path and this path and this path and Similarly, the derivative with respect to ht has the contribution of this path and that path and that path. If you actually explicitly begin writing these out, it ends up looking really bad, right? And trying to work out the math can be disconcerting, to say the least. Fortunately, and I'm not even showing you how you can compute the derivatives with respect to the weights. So this is horrible, right? Well, guess what? Derivatives are trivial to compute. So on the course web page, I have a little slide deck which tells you it says how to compute a derivative. Take a look at it. You can use it to write your own autodiff, right? And this is how you would do it. So let's look at it from the perspective of code. I'm going to run maybe a few minutes over, stay with me, right? Here's the forward code, right? This is only for reference. You're going to compute the affine combination starting from the top for the forget gate, then you apply the activation. You compute the affine combination for the input gate, then you compute the input, and then you compute the input gate value. You compute the affine combination for the input detector, compute the input, multiply the input by the input gate value. You multiply the current memory by the forget gate value, and then add them up to give you the current memory. The circles are component-wise multiplies. Everything else is a matrix operation. Okay, and then for the output, similarly, you compute an affine combination for the output gate, compute the output gate, put it through the tanh. This is just the sequence of operations for the LSTM cell. Now look at the sequence from top to bottom, right? When you compute your backward derivatives, you're going from bottom to top. So in the derivatives, I have this spread over many slides. Here's what I can do. The blue lines basically give you each of the operations going backwards. Okay. Now, in order to compute the derivative at any time, so if you have an LSTM cell, you have the derivative of the divergence with respect to the memory at the next time coming in. You have the derivative of the divergence with respect to the hidden value coming in, which also went up or to the side, right? This actually went both ways. And you have those are the two things. These are the three things coming in. Now something happens over here. This guy, as it happens, CT is updated and used to compute other things downstream. So the information that comes in here is actually just a partial information. It has to be updated in the code. That's something you can just keep in memory. So all of the terms that you see, I'm going to assume that I initialize all derivatives for the entire network as 0. And every single thing can be thought of as a plus equals, an incremental update, as opposed to just freshly computing the derivative. All right. Now look at the first term. I have h equals O times tan c, right? I can compute the derivatives going backwards. If I have the derivative with respect to h, which comes in, because h was the last thing that was computed, right? Then I can say the derivative with respect to O is the derivative with respect to h times tan c, right? The derivative with respect to tan c is the derivative with respect to h times O. The derivative with respect to c is simply the derivative with respect to tan c times the derivative of the tan h itself. So just going back stepwards, right? I've literally just written the operations in reverse. Then the previous operation is O is sigmoid of 0, right? So I can simply write the derivative with respect to 0 is the derivative of with respect to O times the derivative of the sigmoid. Just one step back, right? Then below that I have the affine combination. If I have the derivative with respect to 0, because as you go down, all the derivatives required have already been computed. So I'm literally just writing down the equations and flipping the order, as we saw when we were talking about CNNs, to compute the derivatives, right? So the derivative with respect to CO is simply going to be the derivative with respect to 0 times the corresponding weight. The derivative with respect to H is simply going to be the derivative of 0 with respect to 0 times the weight, and so on. Then I can also compute the derivatives with respect to the weight, going back in exactly the same way, right? And these should have all been plus equals because you're incrementing them. But anyway, so then I go one step up in the forward code, and there's this equation, and I can compute all the derivatives going backwards step by step. And it's very mechanical. You don't even have to think very hard about what it is you're actually doing, right? And you can work your way backwards through the entire code, forward code, to compute the derivatives all the way to the input and return those guys. So these are the derivatives for a single cell. All right? And now I can plug this business of computing, of transmitting the derivatives backwards through an LSTM cell into a higher level code, which is fairly trivial. I just, this is the forward code for reference, right? The backward code is going to look much the same. I would have the derivatives initially. At the output layer, I can compute derivatives as usual. All that happens is that when I'm going backwards, at each point I'm passing all of the current derivatives into the routine that computes the derivatives for a cell, gathers positives, partial terms, and keeps passing them backward. I won't explain the code too much, just take a look at the slides, but the slides are fairly self-explanatory. And also take a look at this extra handout that I told you is on the website. Now one final bit, you can actually simplify the structure. The whole thing is very complex and maybe it's overstated, right? Why do we have so many gates? Why are we sending both the hidden value and the memory into anything when the hidden value is just directly computed from the memory, right? What is the point? Why do we need so much extra computation? Turns out you can simplify the whole thing through this simplified model called the gated recurrent unit, where you combine the forget and input gates. You say if a new input is to be remembered, then it means old memory must be forgotten. So the forget gate is going to be 1 minus the input gate. Very simple, right? So you got rid of an extra gate. You also don't store a compressed and a raw version of the memory. You only store the raw memory. Always operate on the raw memory. And anytime you want to compute things, you work directly off the raw memory. You don't bother with using a stored compressed version of the memory as a hidden state. The raw memory itself is the hidden state. Greatly simplifies things, right? Turns out GRUs work even better than LSTMs in many cases because they're somewhat simpler and more follow the original rationale much more closely. So here are all the equations for the LSTM. Typical architectures, you can have many layers of LSTMs as before, just like in a standard recurrent network. You can have bidirectional structures. All of these follow the same kind of logic that we had earlier, right? These are just like recurrent networks, except that you're replacing the simple activation in a standard recurrent network with this LSTM cell. And the derivatives are also similarly modified. So the story so far, RNNs are poor at memorization and suffer from the vanishing gradient problem. So LSTMs are alternative formalisms where the memory is made more directly dependent on the input rather than network parameters. But otherwise the operations are the same. There are issues on how do you compute the final divergence, how do we use these networks, and so on. We're going to see these and more in the next couple of classes. If you have any questions, post on Piazza.